So thanks for all of you to be here. So my name is Michael Herbst, as you might know, and I'm from EPFL. And this is Paul. Paul is from the University of Aachen, where I basically did my postdoc. And Paul basically is the master student that I supervised. And essentially today we are presenting Paul's work, mostly. I mean, I helped a bit, but it was mostly him. I really should say that. All right, so we're going to talk about surrogatizing quantum spin systems, in particular using reduced basis methods. I will explain what both of these things are. But before we go into the details, I think even though we have a pretty wide audience, it would be quite nice to give a little bit of a general motivation for quantum, right? So why do we care about quantum effects? And I mean, I just make this proclamative statement here, quantum effects are everywhere. So in particular, what I'm talking about is like if you want to understand how solar cells work, if you want to understand how batteries work, microchips, all these things. I mean, quantum computers is a lot what we heard about in the previous talk. There was a whole quantum session, as you might know, at JuliaCon, right? If you want to understand new materials, basically come up with new solutions to the problems that we have in the 21st century. This is where quantum effects really play a role, because nowadays you have to understand when we talk about renewable energies, we talk about, for example, finding new materials for quantum computers. In the end, we really need to, we're fundamentally limited by the materials that we have at hand to solve these problems, okay? So therefore, really coming up with fundamentally ways to understand quantum effects and, therefore understanding basically the basics of physics gives us new techniques for finding these materials and therefore making a step forward with the challenges that we have as a society today. And I think one point, just to make this extra clear, is that some of the supercomputing systems I know, about 50% of the computational time is spent just for quantum chemistry simulation. On top of that comes a fair share for quantum physics as well, right? So this sort of stuff that we will be talking about today, that also the other speakers of the session have been talking about, this is really something that happens and, happens to a large fraction. Okay? So, now a little bit more closely to the subject of our talk, quantum spin models, right? So why should you care about quantum spin systems? So in the end, these are really, I would say real models, right? So the idea is you talk about small spins that are arranged in certain lattices, for example. So these are real systems you can manufacture. So there's experimental techniques to really arrange spins on a particular, in a particular order. And as we will see in the next slide, there's a number of parameters that you can really experimentally tune. And the point is really that, therefore, these systems are small, they're simple. Sometimes you have analytical solutions, but at the same time, you can really probe it. So it's an ideal way for like an analogous system, if you so wish, to make the connection between physics and experiment, like theory and experiment, and understand how you can model new theoretical problems in an efficient way, for example. Okay, so I really like this idea that, in fact, a lot of these quantum spin systems also reflect more complicated systems. Essentially, they are a condensed form of quantum effects that you can also have in real materials, like in materials that we want to synthesize and use today. So therefore, it makes this nice bridge between something which is simple enough that theory and experiment can directly access it, but complicated enough that we can really study computational phenomena, quantum phenomena, which we don't understand yet. Okay, so one thing in particular that we want to focus on is something known as quantum phase diagrams. Don't look at all the details in the slide too much. It's just basically to give you a little bit of an idea. So the point is that in this particular setup, it's a so-called Rydberg chain. In this chain, we have a number of atoms which are arranged, in a chain. Okay, so far so easy. And the idea is that these atoms have two states, basically eigenstates, and they can interact in a particular way. So the details I don't want to explain here. The point is only that the laser field that you use to set this up and, the interaction strengths and so on, these are all parameters of your setup, okay? And essentially, depending on how these parameters are chosen, you get certain ordering patterns, as it's known, right? So here you see that sometimes all the atoms are green, which is supposed to say they are in the ground state. Sometimes you have some patterns that arise. And this is essentially the trick, right? You have certain so-called phases in which one of these patterns essentially are the dominating pattern. And understanding which parameters to choose to get these phases is something which is of interest to understand quantum physics. And yeah, Hamiltonian then pretty much looks like this. So it's a big object with many parameters. And what we are in particular interested in are the eigenstates, right? So the eigenstates of this complicated object for each of the parameters. Okay, so basically for each of these parameters in this two-dimensional space, we want to understand the respective eigenstates. Now, if we really want to do it, we are faced with a big problem. And the problem is that the dimensionality of the Hamiltonian is exponentially scaling with the L, which is here, for example, the size of this chain. Which means that if we really want to do this at every parameter point, like we want to find this ground state, for example, this state at every parameters point, this is really expensive. So typically this takes like a few hours to compute such a ground state exactly, or well, approximately really. And what we want to do in this work in particular is to exploit that, you know, if you are at two close by parameter points, the states typically don't change that much, meaning that they are not linearly independent. So we want to use this to avoid the need to really compute this at every parameter point. And this leads quite naturally to the so-called reduced basis methods. And what we discuss in the talk today is really how you can combine reduced basis methods that I'll describe in the next slides with matrix product states, one standard technique to obtain such ground states. Okay, so why do we believe is there this potential for the reduced basis methods? Well, basically, as I said, the idea is that the states are similar across a phase when you vary the parameter only slightly. So if we basically use very carefully selected points, only a small number of them where we evaluate it, this should give us enough information to sort of interpolate everything, okay? And I mean, these type of reduced basis ideas have already been exploited extremely successfully in the context of PDEs. So, and I mean, also in nuclear physics. So the idea is, can't we use it here as well? And just sort of one idea why this should work is, I mean, so we tried this, and it turns out, for example, if you look at the singular value decay, meaning like the similarity measured to an extent between the different eigenstates that you find at the various parameter points, you find to get a certain accuracy, the sort of number of points that you really need to keep scales much less than the full dimensionality of the Hilbert space. And here you see, for example, the decay of the singular values, right? So this is just from a mathematical point of view, an indicator that this should work. Okay, so if you don't understand this, it's not really too much of a problem. The point is this really tells us there's something to be gained. Okay, so how does this work? What do we actually do? Basically, there's two stages, the so-called offline stage where we put in all the effort. So we will solve really this full problem at a certain carefully selected number of points. And then the so-called online stage where we basically have the solution and just use it. So in the offline stage, for example, here we have a grid, like a small grid of parameter points that we give to our algorithm. And iteratively, basically, the algorithm selects one point at a time to add to this reduced basis. So in the end, we don't do all the computations, only a selected number of points. And essentially, we follow the so-called greedy strategy, which means that we have an error estimate that I will briefly discuss on the next slide. And this error estimate, we just evaluate at every parameter point, and then we find those points where the error is largest. And these are the ones where we really go into the effort to solve with DMRG or MPS ansatz our full problem. And we only do this as a small number of states. So instead of something like 100 to 1,000, we only need to do something like in the order of 10. Or maybe sometimes 40 or something, right? But not 1,000, that's the point. And once we have done this, once we have built our reduced basis, this is now our approximation for all the ground states. So basically, whatever value of the parameter point you want, we use this ansatz with the states that we have actually computed to evaluate independently of the size of the Hilbert space at every parameter point, a quantity of interest. Okay, so one more slide to just make this more clear. So how is really the next parameter point selected? So given that we have already n points, the n plus first point is really selected by this greedy condition. So where this error estimate here is the largest in all the points that we consider. And for the error estimate, we just take the residual for the eigenproblem. And this is, it's a bit surprising, but it turns out you can actually evaluate this independent of the size, like at the scaling independent of the size of the Hilbert space, which means that evaluating this at every point in your testing grid is actually cheap. So the only The only expensive thing is once you have decided which next point you add to your reduced basis to really solve the full problem. That's the only expensive step in this. Okay, so I'm going to skip this for time. The point is, if we now have such a reduced basis available, then once we know this approximate basis in the online stage, we can just use it. So now we can, for example, use it to express any observable that we are interested in, and essentially, like by use of this reduced basis, these snapshots that we have obtained essentially recover the information, at any parameter point that we desire. And indeed, the point is again, this is independent of the size of the Hilbert space in terms of the computational complexity. Okay, so before I hand over to Paul, now, like, what is the sort of requirements for a method that actually computes the exact ground state? Well, I already mentioned that we are doing this with DMRG, but we also use the standard exact diagonalization techniques. So what is required is really you need to be able to compute overlaps efficiently between the states at different parameter points, and you need to be able to compute matrix elements like this, which means that if you think about DMRG, the typical thing to MPS overlaps is doable. MPS MPO contractions is what falls in here. That's also doable. And what is also necessary, because this is sort of an approximation on top of the approximation that you're using for the ground states, you need to be able to somehow control the accuracy of the ground state solver. Okay, so for ED, that's of course just the threshold that you're using for your tolerance, for your diagonalization. And for MPS, this is the standard things like bond order or whatever tolerance you have for your alternating least squares. All right, so that comes to the end, and from my point, and I hand over to Paul for giving you some ideas about MPS and the results.
All right, so also hello from my side. I guess before we go into the results, what this reduced basis stuff can actually produce in practice, I guess we quickly rehash again something we also probably saw yesterday. So what are matrix product states? So everybody knows what we're talking about. So matrix product states are a way to parameterize basically many-body states by taking linear combinations of many-body configurations, and you have coefficients which you express as products of matrices. And you also have this diagrammatic representation on the right, which we also saw yesterday, so I won't go into much detail. But basically, it's a way of writing many-body states. And you could ask, okay, why would you want to do this? Because it initially seems more complicated. And the reason is that you can basically control this problem that you have, that the Hilbert space becomes really high-dimensional, by basically low-rank approximating these matrices you have in your state. So you make a low-rank approximation of them. And this ansatz is particularly effective for one-dimensional system in the sense what Michael already talked about. You have one-dimensional lattice of particles. And this has to do with the underlying entanglement structure of one-dimensional ground states. And in practice, what this means is that this enables us to basically study larger systems, which translates to more physically realistic scenarios, or interesting scenarios. And so the last thing we need to know is what is DMRG, and that's basically just in our context way to obtain a ground state in MPS format. And just to give you a small detail, it's just by basically iteratively optimizing these matrices towards the ground state as to minimize the ground state energy over the MPS manifold. Anyway, just quick recap on MPS. Okay, so in order to see what this method can do, we need to look at some kind of physical system, and we look at quantum spin models, and in particular quantum spin chains, so one-dimensional models. And what we have here is the so-called Haldane chain with spin 1 particles, and we have two types of anisotropic terms. So we have two parameters D and E, and maybe in this context, it's just important to know that we use it as a benchmark system. The phase diagram is already known from previous DMRG studies, and it looks something like this. So we have these Néel-ordered phases, which is basically anti-fragmatic ordering, and we have a Haldane phase. But what that physically corresponds to, I guess, it's a bit out of the scope for this talk. But let's see what the greedy method, this reduced basis method, actually does. So we take this Hamiltonian, plug it into our method, and what we first look at is what parameter points are actually selected. So again, remember we have this greedy algorithm that kind of selects iteratively parameter point after parameter point, and then extracts a snapshot, so solves the stationary many-body problem. And these dots on the phase diagram indicate which parameter points were selected. And what we already can see is that basically in the Haldane phase and also across phase boundaries, we tend to sample more densely. And this is kind of interesting because it seems that this greedy algorithm already understands something about the underlying physics of the Hamiltonian. And so yeah, that's the first thing. And then we can also plot on top of that the residual, which is this kind of error estimator which evaluates how good the reduced basis performs. And it looks something like this. So we get these nice wave shape like patterns. And what we can also see is that close to the snapshots, we get these areas where the residual is low. So basically that corresponds to parts in the phase diagram which this reduced basis model emulates particularly well. Okay, another interesting aspect about this is that now that we have an implementation using MPS, we can go to slightly larger, like very much larger system sizes with exact diagonalization techniques. And what we look at here is that we want to know how does this reduced basis space actually grow as we increase the system size of our spin chain. And in the case of this Haldane chain, we basically look at, we assemble reduced basis for different system sizes, and then we look at how this residual decays. And I guess unsurprisingly, for larger system sizes, the decay rate decreases. So we basically need more snapshots to reach the same level of accuracy. But the cool thing is that here, what we see on the right-hand plot, if we rescale the axis by L to the power of 0.8, kind of all these curves collapse onto each other approximately. And what this means is that basically at fixed residual or fixed accuracy in that sense, this reduced basis space kind of the dimension grows sublinearly as opposed to the exponential Hilbert space. And that's already quite remarkable, I would say. So we really have like an effective low dimensional space available. And what we conclude from that is that basically as we go to the thermodynamic limit, as in we go to infinite system size, we do need infinitely many snapshots kind of to construct a basis. However, due to the sublinear scaling, we could still reach fairly large system sizes, approaching the thermodynamic limit. Okay, next we want to actually see, does our method produce reasonable physical results? So we look at observables and in particular correlation functions. And so what we see here is, for those that don't know what that is, basically we take second order moments of this ground state ordering. And basically by looking at, if 2 points on this ground state are correlated, we can kind of detect different types of orderings, which Michael already kind of showed in the beginning, that there's kind of different ordering patterns. And so here in this leftmost panel, we see basically that, if we measure this SZ operator at 2 points on the spin chain, we kind of get a finite signal in this one phase and is black everywhere else. So we have like this order parameter that really indicates that, we have like a certain type of ordering in this phase. And the thing is that it does correspond to, the previous results from, previous high accuracy studies. And I guess this is also true for all the other observables that we measure here. So for example, if we measure spin operators in y direction, we kind of detect this y-nail phase, and then there are quadruple operators, and also on the right side we have string order parameters that detect the Haldane phase, but I guess that's detailed physics which is not relevant here. But the bottom line is that, in this case, in this benchmark model, the reduced basis method produces, fairly accurate and correct results. Okay, as a quick preview, we also study a bit more complicated systems, and in particular this bilinear biquadratic chain, which kind of is an extension of the previous chain, so it's still spin 1. And this has also been studied quite extensively using DMRG and also analytic approaches. And the phase diagram is fairly complex, and I also don't want to go in detail here. But what we found is that, this being able to basically scan large parameter domains and resolve the physics is actually quite useful to explore parameter spaces, in particular when there's like unknown features. And what we found here, even though this has been studied before quite a bit, is that in one phase, which is also kind of indicated by this clustering of snapshot points, there's like this so-called incommensurate phase, which was previously overlooked. So, this approach is really useful kind of for exploring phase diagrams. But yeah, I won't go into further detail here. Okay, then let's talk about the code side of things. So we coded up this package called ReducedBasis.jl. And it comes at no surprise that this is written entirely in Julia. And for all the matrix product states in DMRG functionality, we use the ITensors package, which I guess many of you are very familiar with. And so the idea is that we implement reduced basis methods for parameterized eigenvalue problems. So as opposed, I guess, to parametrized differential equations. So this is only parametrized eigenvalue problems. And in particular, we have a focus on quantum spin systems, so many-body Hamiltonians. However, it's quite customizable, I would say. So we can use different solving methods, right? So we can use some type of iterative eigensolver, so exact diagonalization in physics terms, or we can use tensor network methods from ITensors, but we can also implement custom solvers quite nicely. Then we also have custom error estimators, so we're not only restricted to this kind of residual, and also more technical stuff like orthonormalization techniques, grid types, and also the assembly strategy. And if you want to have a look, we have the code base on GitHub. And yeah, so the question is, why is Julia like well suited for this project? What does it bring to the table? And maybe the first point I want to make is that it's kind of cool, this project, that is Julia was really suitable like for the multidisciplinary aspect. So it started out with Michael and Benjamin Stamm, who is a professor in numerical analysis and also collaborator here, coding this up. And even though I think Benjamin didn't really have previous Julia knowledge, he was still able to contribute. And then I picked it up, and I'm just a master student, and I also didn't really have previous Julia knowledge. And then even in the end, Stefan Wessel, who was a physics professor and also collaborator here, and my supervisor, he even like contributed to the documentation, even though he had also not written any Julia. So we had this process of like gradual improvement from people across disciplines, and I guess like different aspects of Julia make it really accessible and easy to contribute. So yeah, that's the first cool thing about it. And then I would also say Julia is a highly productive language, so we were able to prototype this pretty fast. So I guess we had the first functional version after a few weeks, and even though I was a beginner, I would say. So yeah, that's also quite cool. And I guess like this point everybody makes is that this generic type system and composability of Julia is just amazing. And in particular, in our case, it made customizing the code quite easy. And in particular, the generic mathematical structure that this reduced basis theory has translates very well into generic Julia code, with generic types, right? And to make this more concrete, I have this quick example, like the simple example. So basically, at the center of this reduced basis stuff, we have an assemble method, and this assemble method takes different types of things, but mostly the most important things are just take a Hamiltonian on which we assemble a reduced basis, some type of grid, some type of information about the greedy assembly, and a solving method and some technical stuff, which is not important here, but solving method as an iterative solver or DMRG or whatever. And the thing is, it basically all calls the same generic method, which is pretty close to the pseudocode, which you write down in like a numerical math paper. And however, then when you go further down the line, there are solver-dependent subroutines, and these then call specialized methods via multiple dispatch. I guess like this is a pattern which frequently comes up in Julia code. So for example, whenever we compute like these reductions to reduced basis space, which frequently comes up, what can happen is that this translates to actual matrix multiplications if it's a matrix made out of numbers, but it can also come down to MPS, MPO, and MPS constructions if H is an MPO. So, this boils down to different methods. Right. Okay. This brings us to the conclusions. Okay, so this method, this reduced basis approach, is really, really nice to kind of explore and efficiently capture phase diagrams. It's quite cheap actually. It's kind of difficult to quantify reasonably, but if you like compare directly against, like, let's say only using DMRG, you kind of gain a few orders of magnitude and kind of speed up if you like just use this for like scanning phase diagrams for quantum spin systems, but this probably also extends to like more quantum many-body systems. And in particular, by using matrix product states in DMRG, we were able to do this for larger systems as previously possible. And what's also kind of cool is that we basically, these surrogate models, these reduced basis models, are mathematically justified in the sense that we build on top of mathematical theory that's been around for quite a while. And we have error estimates and so on. And so one could also imagine that we could build from this like an automated parameter space exploration for basically Hamiltonians that we where the kind of phase diagrams are known. And of course, you can also like simply integrate your favorite solver of your choice. So the obvious choice would be try to plug in other kinds of tensor networks. Tree tensor networks would be relatively easy because you can track them exactly and so on. But you could also use GPU-based solvers or quantum Monte Carlo solvers in some cases. And again, we have the code base on GitHub. And if you want more info on also like the physical details, you can check out our preprint on archive. And lastly, we come to the acknowledgements. So our collaborators, Stefan Wessel, Matteo Rizzi, and Benjamin Stamm. A lot of thanks to them. Also from my side, special thanks to Stefan for actually making it possible for me to come here. And I think that's the point where I hand over to Michael again for some advertisements.
Yeah, because I'm also in the fortunate position that I recently got a junior faculty. And basically, if you're interested in these kind of things, please let me know. I have some postdoc and some PhD positions. And with that, we look forward to your questions. Thank you very much.
Thank you. Let's open up to questions.
So could I think about this reduced basis like a perturbation theory in the states which I already found, so to say, in the surroundings?
Interpolation, rather. You can actually do perturbation theory on top. We haven't done that yet, but that is actually something that comes on top. Yeah, it's more an interpolation between what you have. Yeah.
So in that case, if you go across a phase boundary, it probably doesn't make sense to use the reduced basis from the other phase, right?
Well, the funny thing is with this residual error, the reduced basis will notice that there's a new phase and will do a computation there. So it actually has a state in both phases. And so we'll sort of use the left-hand side state to extrapolate from the left and the right-hand side state to extrapolate from the right. So here you see, Paul, you should explain this. It's your plot.
I can also explain this. So basically what you can see here is, maybe this is a bit too much at once, but what you basically see is that around each point you solve, kind of the most like dominant area where this particular ground state kind of dominates the surrogate ground state you construct is, is built like these Voronoi cells. And what you can, I guess, see across phase boundaries is that you basically have like cells that kind of split at the phase boundaries. So you kind of write that across phase transitions, you need ground states at both points to like correctly resolve it. So in that sense, you're right. But the cool thing is that this like greedy technique, which selects the parameter points, tends to pick up on that. There's no guarantee, but it tends to pick up on that there's like a strong variation across phase boundaries. So it tends to sample both sides, and then you can kind of interpolate between it.
Okay, cool. We have time for one very quick question and answer. If not, let's take the speakers again.